let me introduce our 6 invited panelists. Professor Yoshua Bengio is here, right? And Professor Jan LeCun is here, okay? And Professor Chelsea Finn is here, and Dr. Tara Sainas is here, and Dr. Jen Waltman Vaughan is here too. Lastly, we invited a special guest, Dr. Inyop Kang, the president of System LSI business of Samsung Electronics. Dr. Kang, could you introduce yourself shortly?
Yeah, this is Inyop Kang, the General Manager of System LSI division in Samsung Electronics. It's my great pleasure to join this forum. Let me go by saying I feel like standing on the shoulders of a giant. Thank you.
Thank you. So for the discussion, there will be a natural way to discuss, but we prepared short discussion items pre-hand. So let me start with some suggested discussion topics first. Let me talk about question on big neural net models, which is a hot passion now. As shown by GPT-3 of OpenAI, bigger and bigger models are being developed, as you know. Can we handle this explosion with current computing hardware of deep learning, such as GPU, or do we need new architectures of computing? Any ideas?
Hello. I mean, it depends if you're working in academia or industry. And so if you're in academia, I can tell you that we would really appreciate some progress on the hardware to be able to run larger models and learn on the scale of things like GPT-3. On the other hand, what I'd like to add is there are lots of very exciting and important research problems that we can address without having that kind of computing power. If you look at some of the open problems that I discussed in my presentation, many of them are already challenging, even in very simple environments. And so, yeah.
Okay. So, Dr. Kang, as a head of making processors, do you have any idea about this evolution of
I need to understand the amount of horsepower they use in the GPT-3. All I know is they used 175 billion parameters. Anybody has an idea what kind of hardware they use or how much money they spend? Depends on that one. I could answer, I guess.
So it takes a lot of resources, and the specific number is not known here, but people say that the cost of training GPT-3 is more than 1 billion, not 1 billion, but $100 million.
The parameter they said is 175 billion parameters.
Yes.
So I'm just wondering, there's a trained parameter, I assume?
Yes.
But what kind of hardware they're going to use for the interactive the NLP is sort of should be real time. So I'm just wondering. So, and then somebody criticized GPT-3. They are lacking causal understanding. Even though some others say it's wonderful in terms of article writing. It's hard to distinguish whether it's from real human or not. But I have a little idea. But at the end of the day, I think we need one more step, not just like a current approach.
Right.
I mean, that's why Professor Bengio is working on System 2, right?
That's right. So, in that case, let me go to the related topic with this question. So, the idea is that could modularity and compositionality of neural net be a way to overcome this big computational bottlenecks of big models? If so, could neural net modules having different functionality be emergently discovered in self-supervised way? Is that, do you have any word on it, Dr. Bengio?
Sorry. Yes, I think the main advantage of modularity is for out-of-distribution generalization, right? So if you can decompose the knowledge that is learned in pieces that can be recombined, especially in novel ways that may have not been seen during training, then you're increasing your chances of being able to do out-of-distribution generalization or fast adaptation. And we now have a series of papers suggesting that this hypothesis makes sense and that you can get better transfer learning or adaptation or even zero-shot generalization. But it's not easy, and I think we're just beginning to explore these kinds of architectures. Another interesting connection is between modularity and causality, because if you study a bit of the causality literature, what it tells you is that there is, in principle, an ideal, correct way of decomposing knowledge into pieces corresponding to the underlying mechanisms, the so-called independent mechanisms that can be separately learned and sort of factored from each other.
Maybe this kind of modularity can help the intelligibility itself of these models, because the big end-to-end models like GPT-3 it's very difficult to understand what's going on inside here. So, okay, any other?
Yes. Yes, I think that this kind of modularity may also not be applicable everywhere in the system. Like, what's plausible is that you only are able to do it at sort of a high level of abstraction for the kind of knowledge that we communicate with language, but it may not apply for things like perception, for which it might be potentially intractable to get the sort of interpretability that allows us to explain with words what we're doing and how we're reasoning.
Okay. Let us talk about a little bit more about these big models. So as Dr. Kang mentioned, GPT-3 has 175 billion parameters, and it shows amazing versatility already. But human brain is a lot larger. Human brain is known to have 100 trillion synapses. If we scale up current neural nets up to the level of human brain, could we achieve human-level performance? Some people argue that, but do we have to focus on scaling, or rather than searching for new algorithms and new architectures at this point? Do you think?
Let me
okay.
If my daughter always said that on this kind of question, my daughter's answer was BOTH, both. We gotta try both.
Yes, we have to go both.
Either one. Yeah, sure thing. As a matter of fact, since I'm gonna have this forum, I calculate based on the known literature how many the cortex neurons we have, how many synapses, human synapse around 15,000 connections per neuron, and calculate how much money do I need, how much silicon area I need. And then roughly, it depends. It depends on scaling. It requires 1 kilometer square to 10 kilometer square. It requires $100 million to $1 billion. So that's a very back of the envelope calculation. So eventually we'll there, but I'm kind of doubt we can achieve a human level using existing silicon technology. So in that sense, definitely we need to have new algorithms as a complexity reduction, I think.
If I may answer that question. Can you guys hear me okay?
Yes, we hear you clearly, yes. Although we don't see your face.
I know you can't see me, and I'm not sure why, because my video is on, but somehow it doesn't show up. Anyway, I think we're missing some major pieces to be able to reach, human level intelligence or even sort of animal level intelligence, like, the level of a cat or a dog. I think we're missing some, very basic principles that we haven't yet discovered. And it's not just a matter of scaling the methods that we currently have. A cat brain has about 800 million neurons, so it's not that large. We might have machines in the near future that are able to reach that scale, even though the number of synapses is very large. But the point is that we just don't have a good idea for what learning algorithms nature uses. And the type of the paradigm of learning I talked about in my talk, self-supervised learning, is not something that we're doing very well with machines. We're not able to really reproduce the type of learning that we're observing in animals and humans. So until we figure this out, I don't think we have any hope of kind of reaching the type of intelligence we observe in animals and humans.
Yeah.
I agree with Jan that there seem to be fundamental things that we are missing. I think that GPT-3 systematically makes certain kinds of mistakes that won't be addressed with a larger model. In particular, as one example, I think we need to think more about the data that these systems encounter. For example, if something changes about the world, like the COVID-19 pandemic, a static GPT-3 model will not be able to intelligently speak about some of the things that have changed without completely retraining the model on all sorts of new data. And GPT-3, for example, doesn't know how to interact with humans in a way that allows it to adjust its knowledge. And it doesn't have an understanding of the consequences of what it says, kind of a sort of like sequential decision-making. So I think that there's all sorts of limitations of GPT-3, especially with regard to the data that it's trained on, that are missing. And we need to be thinking about, I kind of agree with the sentiment of trying both scaling models more and trying new techniques, but I think that we're not going to get there with just scaling.
Yes.
Question then. So you guys think inferencing-wise, we're in good shape. But training, there's a massive network. We have no idea. That's what you guys say, right?
I think what Jan and Chelsea are saying, and I agree with them, is that even if we're able to scale up even more than we're doing now, we would continue having diminishing returns and never converge to something, anything close to, say, what a 2-year-old could do. And as Chelsea was saying, part of it is because there's a lot of knowledge about the world that, say, something like GPT-3 doesn't have even access to. I mean, just training on text does not allow the machine to understand how the world works, because there are a lot of things that we can't about, a lot of knowledge in our head that is not verbalizable. And so we can't write it down. And so GPT-3 can't learn about it. And so if future systems that have intelligence comparable to a child or an adult will need to build a world model similar to what Jan was talking about, understanding how the world works, mostly in an unsupervised way. I think they will have to be like babies and go after that knowledge in an active way. But in any case, it's a lot of open questions that we still have to study, and we have no clue when it's going to be solved.
Okay, so we have a related question about how can we bridge the gaps between the current technology and the future of human-level intelligence. So it says that, what are the current limitations of machine learning, even in the age of GPT-3? What are the gaps between current machine intelligence and real human intelligence? How can we build a bridge between them? It's kind of related with that, right?
I'll jump in here. So in my mind, GPT-3 can generate coherent text, but there's a big difference between language generation and truly being able to understand what it is that's being said, right? And because of this, machine learning models are going to make types of mistakes that are just very different than the types of mistakes that are made by humans. And it's going to have really devastating consequences if these models are used in high stakes scenarios. This is going back to what Chelsea was saying a minute ago, actually, about language models not understanding the consequences of what it is that they're saying. Language models are known to generate text that's offensive or text that is even dangerous if we're thinking about something like a medical application. So in my mind, in the short term, at least, rather than just trying to go for technical approaches to try to bridge this gap, I think we need to go for more social approaches as well, and think about things like adding human oversight if necessary, if we're thinking about using models in something like these high stakes applications.
Maybe I can add to a little bit of what Jen said as well. I think a lot of these machine learning models that we're looking at, they are great at memorizing the training data that we give it, but they don't generalize well to, like in speech recognition, they don't generalize well to words we haven't seen. And so, for example, we see with our end-to-end models, they do great on the 200 million examples that they're trained with, but you give it some out-of-domain vocabulary word and it can't even recognize it. Whereas humans don't have that same generalization problem like these end-to-end models do. So another challenge is, how do you adapt or inject knowledge in a quick way without having to retrain a whole model every time there's a new word that you don't get right? And this is challenging.
Dr. Pancio, you have a few words.
Yeah, I mean, I agree with everything that was said, and I want to make a connection with what we talked about earlier with GPT-3. So, as Tara said, and you know, very much in line with Chelsea's talk, one of the big gaps is fast learning of new tasks, or even zero-shot generalization. Humans are very good at that. We are faced with a new environment and we kind of understand what's going on, even though it doesn't look anything like we've seen before. So it's not a matter of scaling here, right? It's not like we're not interested here in the asymptotic performance of if I have zillions of examples of the same distribution, but rather how you can face a new distribution, a somewhat different environment. Or in the case of speech, as Tara was saying, even the tail of the distribution is something like kind of exponentially rare individually. And so, yeah, scaling is just not going to cut it here. And we have to solve these problems, including the understanding problem, which has to do with understanding how the world works, related to causality and related to capturing the dynamics and decomposing knowledge in the right pieces. All of these things are not about scale. At some point, of course, when we want to deploy models that are understanding our world, and our world is extremely complex, we will need scale. But before we get there, there's a lot of basic science that needs to be done that could be done on a small scale.
I agree.
I completely agree with what's been said so far. One additional thing that I'd like to put out there, and one kind of additional thought is, I work a lot on robotics and actually trying to translate these machine learning techniques to build a physical robot that can operate in the world and do basic tasks in the world by interacting with objects. And while we've seen really impressive feats in AI and machine learning, from things like GPT-3 to playing chess to playing Go and so forth, we still don't have machine learning technologies and artificial intelligence capabilities of enabling a robot to make a bowl of cereal or drive to the grocery store. Like these really, really basic things are still beyond what our current algorithms are capable of. And I think that this is evidence to the fact that we're missing something fundamental about some of the things that are just so easy and intuitive to humans are actually so difficult for artificial intelligence systems. And we need to be thinking about how we actually solve the things that are easy for humans to do, like being able to generalize seamlessly to new environments and interact with objects, more so than figuring out how we can build very specialized systems to solve one task.
Great. So
Let's have some speculation. What are those missing links? Or you guys should try more. Oh, yeah, your video is on now.
Yes.
Or you guys should study primitive animals, trying to guess what are those missing links, like a neuroscientist?
Well, this is pretty much the content of our talks, actually.
I'm sorry. I mean, in a gist, in a single sentence, what are the speculations? I mean, they wanted, you guys said comparing to Homo sapiens, but if you compare to a very primitive one, we could guess, right? Some of the maybe the pre-programmed through the evolution link or whatever, right? At the end of the day, isn't that just the connection of atoms or molecules? That's it, right? If you think materialistically. Nothing else. There's no spirit, let's say.
We don't know.
So you know, in his talk, Jan insisted on the ability to learn from observations is something that we don't do nearly well enough. And Chelsea talked about the ability to learn from very little new data by almost learning how to learn. And I've talked about how being able to generalize quickly might be one of the advantages we get out of conscious processing that's more sequential and that we can verbalize with language. So these are all examples of directions that are actually very closely related to each other that try to address these gaps that we've been talking about.
Maybe the capability of inferencing and the system 2 perspective of cognitive abilities may be a key to the missing link. So let's talk about something about system 2 ideas. The topic is humans have built civilizations by abstraction, such as math and sciences, and we created a lot of rules, such as laws. If we can effectively build AI system who can have system 2 capabilities to build its own rules and abstractions, could AI augment human society itself by providing new abstractions and new rules? It's a kind of futuristic question.
Yes. Well, okay, so first of all, you have to realize that most of our work in machine learning these days is not about learning hard rules. Even the kind of system 2 research that I'm looking at isn't creating the kind of logical, symbolic, very easy to express rules. I mean, we might get there one day, and there are people who are following more of this kind of direction. But yeah, this is science fiction. One thing that maybe is closer to more reasonable and achievable is using the kind of representation learning power of machine learning and deep learning as, if we make progress towards learning like system 2 types of abstractions, is to help scientists come up with abstractions that they hadn't thought about yet, right? So if you look at what are scientists doing, what have they been doing in the last few hundred years? They've been coming up with abstractions that allow to capture, for example, causal structure in the world without having to go into all the gory details of with the position and velocity of each atom in the universe. And so these abstractions help to explain things in a compact way that can capture causal mechanisms without having to look at everything else that is going on in the world. And so I'm hoping that the sort of research we're doing eventually could become a tool for scientists to propose hypotheses for new theories or new abstractions that can help to model the world better.
Okay.
Understanding society is much harder.
Yes.
I'm trying, and really I'm about to say it's impossible, but anyways.
Yeah, it's difficult. Okay, my next topic is related with the previous question. If we go back to the history of AI, in the dawn of AI in 1960s, many AI researchers believed hardly in symbolism. For example, the General's Problem Solver by Simon, Shaw, and Newell. it brought along AI winter, and connectionism appears to be flourishing now with deep neural nets. Could we expect the remarriage of symbolism and connectionism in the coming future?
Okay, if I can answer that question, can you guys hear me?
Please. Yes.
Okay, because I had to change computer so that you could see me. So the big question there is, and this is kind of related to the previous question about System 2, is how do we get machines to reason, right? And particularly, how do we get learning machine to reason? So how do we make reasoning compatible with machine learning? And the problem with sort of classical approaches, symbolic reasoning, is that it manipulates symbols with logic, and logic is very highly non-differentiable. So it's essentially incompatible with the type of learning that we're very fond of at the moment. So I guess the big obstacle is how do we make reasoning compatible with gradient-based learning, essentially with backpropagation or something similar to this, evaluating gradients. And that probably means replacing symbols by vectors or tensors or numerical objects, and replacing logic by continuous functions or differentiable functions at least. And long chains of reasoning will be of a different nature, be replaced by dynamical systems and something of that type. And so it breaks a little bit, a lot of what sort of classical AI people have been thinking of and advocating. Now, how to do this is not entirely clear. There's a lot of interesting work along those lines in sort of the idea that if you have a recurrent network, it can sort of produce long chains of reasoning. That you may have recurrent networks that are configurable for the task at hand, and having multiplicative interactions, attention, things like this are things that are very useful for that. In fact, transformers kind of come close to this. So one of the things I said in my talk is that I think, for example, the future of computer vision will combine completely feedforward models like convolutional nets with sort of object-based reasoning on top of it, probably implemented with things like transformers or whatever will come to replace it in the next few years. So that's the kind of stuff I believe in, but it's not entirely clear how to instantiate all of this yet.
Yeah. To summarize, the answer to the question is no. I don't think that it makes sense to imagine that we're going to take the classical AI symbolic logic stuff and just slap it on top of a deep learning. It's just not going to work. And there are many good reasons. So Jan talked about the differentiability and learnability, but there are also other reasons. So one of the fundamental problems with the classical approach is search, exponential cost of search, right? And in the old days, people used heuristics, and they were handcrafting those heuristics. Now, this is something where the modern machine learning approaches based on neural nets and so on actually can be very good at. If you look at how AlphaGo is really structured, it exploits the system one like value function neural nets to cut down the search in multi-color tree search. I think it could be done much more efficiently, but the idea is there, and you need really to combine the reasoning that looks at sequences of steps with abilities to efficiently figure out good candidates for these trajectories. And if you look at human reasoning and human problem solving at a conscious level, we don't need to look at many different paths in our heads when we are like planning. It just comes to us, one or two candidates, and that's it. It's enough, and usually they're pretty good. So that ability to generate good candidates is something that's probably not happening at the kind of symbolic or verbalizable level, let's say, but rather as something that's more like system one and where you can't easily decompose it into small pieces that can be explained.
Okay, thank you.
agree with all of that. I think that there are limitations of deep learning, but the path to addressing those limitations is not necessarily to introduce symbols. Another limitation of kind of more symbolic approaches to add to the ones that Jan and Joshua mentioned is that symbols typically impose very rigid abstractions on the problem that you're trying to solve. But in the real world, we need to actually very flexibly change our abstractions and our representations based on the context that we're in. So if we, for example, have the symbol or concept of a bike, if we are riding a bike, our representation of that bike may be very different than if we're fixing that bike or taking a picture of that bike. And so we need to be able to have this sort of flexibility. And I think that many symbolic approaches don't allow us to have that flexibility.
Okay, the answer is no. Thank you. So next question is for Dr. Bengio. Before the ideas of your neural causal models discovering causal relationship between numerical variables have been tried by many probabilistic approaches, such as Bayesian networks by Dr. Judea Pearl. Could you explain why the new way of neural causal model is promising compared to the traditional approaches?
There are different parts to this answer. So one is very straightforward and would like the causal mechanisms that are the building blocks of a causal model to be sufficiently flexible and using neural nets for these parts seems appealing. So that's one thing. So in other words, the whole causal model is a big neural net that just has a modular structure.
Yes.
Another thing that is missing currently in a lot of the research in causality is, where are these causal variables coming from? So when you're a scientist and you're applying causal science, like if you're a biologist or a sociologist, usually you're going to define yourself what the causal variables are, right? They're going to give them to the model, and these are going to be things you can observe directly. But if you're a robot or if you're a 2-year-old, you just have your sensors and your actuators, and somehow you have to come up with the right high-level abstractions by which you can understand, causal dependencies like gravity and force and stuff. And by the way, this happens well before language kicks in seriously, so before 2-year-olds. So we can do a lot of that causal understanding of the world well before our parents can explain it to us. So it's really unsupervised discovery of both like the mapping between low-level stuff and these causal variables, and at the same time how these causal variables are related to each other. And that's a very tough problem, and we've just started to look at this. But I think this would be a contribution to the science of causality, which hasn't been really looked at in the past, and where deep learning researchers, because they focus on representation learning, could really help to advance the science.
Okay, thank you. So next we go to some general issues of AI. This topic is our society has inherent limitation in fairness. We live in unfair world, actually. Machine learning systems learns from this biased data. How can you make AI fairer? Should we augment the data? Or should we change our society fundamentally in some way? How do you say? Both?
Yeah, so I spend a lot of my time these days talking to product teams about fairness. And one thing I can say for sure is there are no easy answers to this one. On the question of data augmentation, data is part of the problem here, but it's not the only problem by any means. So data augmentation can only go so far, right? really, if we want to build machine learning systems that are fair, we need to rethink the entire way that we're building machine learning systems and rethink who is in the room when that's happening. So right from the start, when we're defining a new product or a new service, we need to step back and assess possible unintended effects and consequences of that service. You know, systems are always going to reflect the values of the people who are designing them. So we need to ask, when we're designing the system, who is it giving power to and who is the system taking power away from? Right? And we should be willing at this point to step back and call off a product or change what we're doing if it seems like the harms are going to outweigh the good, or if we're in a case where the risks are just too high. Just because we can build something doesn't always mean that we should build this thing. There are, of course, things that we can do about data as well. When we're collecting data, we need to think about where this data is coming from. We need to think about the extent to which it represents different populations and where societal biases might be hiding. Are there biases that could arise from the technology that we're using to collect the data? Are there biases that could arise because there are humans labeling the data? You know, at other places in the process, this comes up too. When we're building a model, are there biases coming in because of the way that we've selected features, or because we've chosen a particular objective function that might make some sense for some populations, but not others? I think all of this really requires a different style of thinking than machine learning researchers and data scientists are typically used to engaging in. And this means that we really do need to change who is present and whose perspectives we're hearing when machine learning systems are being designed and when all of these crucial decisions are being made. So we need more diversity. We need to have user researchers in the room. We need to have perspectives from people who will be using AI systems represented and perspectives from people who will be affected by these AI systems. Especially when these happen to be marginalized communities. On the other side of the question, you know, yes, of course, it would be better if we could just change society fundamentally, but this seems a lot harder to do. And there are things that we can do as computer scientists and as people building the systems to make some change.
To add something.
Scheduling algorithm, right? Scheduling algorithm, you have a fairness metric, but how are you going to define the fairness metric? That will be a tough one. I think we got to have a metric first, isn't it? Or we learn the metric somehow.
I think in general, there's actually too much of an emphasis on metrics when it comes to talking about fairness. Just, you know, again, as computer scientists, and especially computer scientists who work in industry and are used to having everything judged by metrics, there's this kind of push a lot of the time to try to come up with metrics for everything. And sometimes this can actually be harmful when we're talking about fairness because, you know, abstraction is not always a good thing here. And if we're talking about systems that produce offensive text or that denigrate people, or, you know, there's just a lot of things going on that you can't cleanly capture with metrics. And sometimes we need to move beyond this.
I just want to add something to what Jen is saying regarding the second part of the equation about society. So many of the things she talked about are about, you know, changing the ways that, say, companies are designing and deploying AI to address some of the fairness issues. But sometimes or often, you know, this will come at a price. And there may be some companies that decide to go ahead and pay for that, maybe because their brand is very important, their public image is very important. But there will be others which won't. And so I think that, you know, society needs to change in the sense that changing the rules of the game, changing the incentive system, the fiscal forces that change the behavior of companies so that they will actually implement those policies that lead to, better protection of the public, making sure that their actions are not going against public good, and so on. So you really also need governments to step in, and today most of them are clueless about how to do this. So this has to be done carefully and probably consulting with the experts. But this is happening all around the world right now. Many people are discussing how this could be done, and countries are trying to align how they could do this. But at the end of the day, I think it's going to be better for companies as well, because at least the rules will be clear, and you won't be kind of in tension between your own personal moral instincts and the urge to survive, which company you're faced with.
Thank you, Dr. Bengio.
I agree with that to a large extent. And even within companies where people have good intentions and, either individuals or higher ups have good intentions, it still can frequently be the case that when people are under a lot of time pressure and need to make a decision about something that is shipping right away, fairness is still kind of the first thing that gets cut if there's no governance in place and no forcing function making this happen. So I agree. I just hope, given that there are really no one-size-fits-all solutions or even definitions for fairness, I hope that if there are external bodies that are making this type of governance that's going to apply to companies, they are not being too narrow in the types of definitions or limitations they're trying to impose. And if anything, I would rather see, this type of regulation around processes or standards around processes that people should follow in the design of machine learning systems, rather than trying to make everybody meet the same mold in terms of outcomes.
So maybe there's a way around this issue of metrics, which are kind of brittle and not necessarily what we actually want. There's a management approach called objectives and key results, which I think is used at Google. And the idea is to define what we want, say, from a subcontractor or from an employee or from a department or from a company from the point of view of society, at two levels. At one level, you have the objectives, which are like principles and are not necessarily very precise, but this is the spirit of the law. This is what you would like the organization to do. And then you have the key results, which are like metrics. There are things that are quantifiable and that the organization is going to try to stick to. But with the knowledge that these these metrics could change because maybe we find that they're not really sufficiently faithful to the high-level principles and objectives. And so you don't want them to overfit those metrics because they have to keep in mind that there's a higher principle that's at stake.
Yeah, I totally agree. And that's very much in line with the way that I've been thinking about these things too. And I think that these key results could sometimes be metrics or could sometimes be hitting the right process points.
Okay. I think we have 5 minutes remaining before the Q&A session. So the next topic is somewhat specific. End-to-end models or sequence-to-sequence models have been successfully applied to machine translation and speech recognition. Samsung is one of the first to apply them, actually. There had been a high expectation that dialogue system could be the next one to apply it, but it seems very difficult now. What field would be the next end-to-end model successful application area?
So I think what you're going to see, so end-to-end sort of really changed speech recognition because it allowed us to do speech recognition on device with the quality of the model in the server, but being much, much faster in terms of latency. And also, not the big thing is we don't have to be connected to the internet now. So basically, we can do speech recognition on device without even having to be connected to the internet. So I think what you're going to see is because of that, because of that sort of breakthrough, the change I feel is in terms of what are the applications going to be going forward. So for example, I think you're going to see long meeting transcription, being able to like having the end-to-end model always on your phone, being able to decode long meetings, long audio conversations. And particularly, how can you do this when the model needs to operate in low power and be always on? So this is one area I see. You can imagine now with COVID-19, you're going to want to do more audio-visual speech recognition. I'm bringing in multiple modalities, being able to do meeting transcription. It's going to be another area. Because we can do end-to-end ASR on device, offline, we don't need to log data.
Yes.
So things like federated learning, how can you train models on device with the data you have? How can you do personalized speech recognition for each individual user? It's going to be another area. And we have seen in some of our research that, we say one model to rule them all, so to speak, that having one model trained on multiple dialects or multiple languages seems to be, at least in small cases, work very well. How do we scale this up so we have one model for all languages in the world? It's going to be another challenging and interesting research area. So I see that end-to-end now is going to expand in many directions because of the new possibilities that it's opened up.
So I think that dialogue is very challenging because it sort of breaks the basic assumption of machine learning that you have a training set and a test set, and you can train on a training set and test on a test set.
Yes,
the dialogue systems are interactive, so the best way to train them is to train them with someone talking to them, presumably a large collection of people talking to the system, and you test it in similar situations. So there's been a very long-term project at Facebook called Parlay, P-A-R-L-A-I. There's a lot of open source code that came out of this project to kind of attempt to change the way we approach machine learning because of this interactivity. It makes everything more complicated. But of course, there is a huge demand for dialogue systems because we'd like to have intelligent virtual assistants, and that's what dialogue system can bring us. Now, there are probably useful dialogue systems that we can have in the near future that will not be able to answer like every question we can ask them, but they will be useful nevertheless. Before we have systems that are sufficiently intelligent that they're not frustrating to talk to, we'll have to have machines that have some level of common sense. And that's taking back to the questions we were discussing at the beginning of how is it that humans and animals accumulate so much background knowledge about the world in the first few months of life, and we can't reproduce this type of learning with machines. So all of those things are going to kind of converge at some point. Whether it's going to be in the next 2 years, 5 years, 10 years, 20 years, we don't know, because we don't know what techniques would be required for this for us to make significant progress in that direction.
Yes. Thank you, Dr. Lu-Kun, and thank you all the panelists. I think it's time to go up to the next Q&A session. First of all, we have received a few questions in advance. The first question is from Sang-Yul Jeon. Are you there?
Yeah, hi.
Please say your name and affiliation first.
Hi, I'm Sang-Yul Jeon and currently PhD student at Yonsei University. And I have a question for In-Yeop Kang, Corporate President. I noticed that the recent efforts of Samsung have focused on MPU solution for on-device deep learning. And recent studies on network compression have shown impressive results, achieving higher speed at lower power. So as a graduate student studying software algorithms, I'm curious about the practical difficulties in implementing this into real hardware MPU.
Yeah, my mind is occupied with the fundamental challenges our friends are confronting, generalization, worldview, everything. And then, so compared to those challenging ones, I think how to implement efficiently, that's relatively easy. Let me put it that way. So especially on the mobile side, we've been working on mobile and data center. I mean, you have a bunch of horsepowers. And then one thing we can do is we come up with the phonetic algorithms, and then we're trying to prune the network, and then we prune the bit width. We quantize it and distribute all over the computing engine we have, CPU, GPU, neural processor, DSP. And then also sometimes we sacrifice with the performance, so-called negligible performance degradation. So up to a certain point, what Terra's working on, like end-to-end AES-on, we could achieve a certain level right now. So we are comparable. But today I realize the researchers not comparable with what's the next. That was interesting to me for today. All right.
Thank you.
Maybe I can add a little bit to your question.
Go ahead. Yeah.
So I think that you will. How do you get these models to obey low latency? So we have all these great research ideas, but they have to fit within the latency constraints. They have to fit within the size constraints. They have to fit within the power constraints. And in the end, we try not to do all this model compression because we have to sacrifice on quality if we do. So what we do a lot of is try to either have specialized hardware so that we can run a lot of the models within the allowed latency constraints, especially like the second pass rescore that I was talking about. A lot of that is hidden behind the first pass, so it doesn't increase the latency. We try other things to reduce the latency of the model, like the endpointer I talked about. We try not to prune because then we will automatically take a degradation in quality. So looking at other ways to reduce latency is an area that our group has been pretty active in.
Thank you. Before we go to the next question, I have a short mention that Dr. Seong-Woo Hwang, the president of SIIT and the co-chair of this program, is also connected in the session. So could you say hello? And no questions from you?
Comment and thank you to all of you. Thank you, Professor Bengio, for organizing all this forum again. And thank you, Professor LeCun. You came back, you kept the promise. You told me you're gonna come back within 2 years. Thank you for coming back. And congratulations, Professor Finn, for Samsung AI Researcher of the Year. And I'd like to thank you, Tara and Jan, for your inspiring talk. Thank you very much. I think the role of co-chair of this forum is to serve you great dinner and wine, but this year I was not able to do that. I'm expecting next year. Thank you very much.
Yes, let's do the next year.
Also, thank you, IK, for participating in the panel. It was great.
Thank you, Dr. Hwang. So next question is from Igor Vasiljov. Are you connected?
Yes, I'm here. Can you hear me?
Yes.
Oh, great. Thank you so much for letting me answer the question. So my question is more general, maybe to all panelists. As we can see, recently many researchers in the AI field are focusing on the system 2, what is reasonable, as we all want to understand and trust the NN. However, as, for example, Professor Tara Sainath showed today, bringing some intentional bias can help for practical solutions. And bias is one of the known and inherited features of System 1. So my question is there any possibility to combine System 1 and System 2 in some smart way to get even higher practical performance? And when I say practical, please consider some limited energy budget solution. Thank you.
Any volunteer to answer this question?
Well, I think the question of bias in the sense that Tara was talking about is something that can apply at all levels. It's really about taking context into account and figuring out what the right context is that should influence the way that you're extracting features and processing them. So it's not specific to either System 1 or System 2.
Mm-hmm. Is it enough for you, Bashirjov?
Okay, we got it. That
my general comment is bias is always evil.
System 1.
I love zero bias.
We have to be careful.
Define the bias. There's a difference.
Okay, yeah. The word bias means many different things, so we have to be careful.
Yeah,
yes,
sure.
Yes, bias in there.
So Jen would use the word bias in a different sense.
Right.
There's also a meaning that I use in my talk, which is inductive bias, which is a good thing, but it's a completely different concept.
In social bias, right? Okay. So let's move on to the next question. Sujong Kim has a question, I heard. Are you here?
Yeah. Hello, I'm Sujong, a PhD student at Seoul National University, and I have a question for Dr. Tara about her talk. According to the last experiment in the presentation, learning different kinds of Indian languages together performed better than learning them separately. So I wonder how the result could be different if the languages are totally different, as like Korean and English. So even in this case, will the co-training still help to increase the accuracy?
That's a great question. So in our research, we're finding that having one model trained on similar dialects or similar languages, then one model on all of these is better than a model in each individual domain. But when we scale this up to completely disjoint languages, we're not finding the same thing. And so basically, we're trying to look at injecting some sort of, or structuring the architecture to be more, let's say, language family specific now. Because just training on, let's say, 50 different languages, even with a very massively large network, we're not able to match performance of each individual domain. So it's still an open and challenging research area.
Thank you.
Thank you. Now I would like to get an open Q&A from other online participants. If you have any questions to any panelist, please raise your hand. Okay, number 4. Yeah, Ida? You're right, Ida, right? Yeah, go ahead. You can start now.
Okay. Yeah, so thank you everyone for all your great talks. Earlier in the year at AAAI, there was an Oxford-style debate on whether AI researchers and academia should focus their attention on research problems that are not of immediate interest to industry. And maybe for our university researchers, it's really how you strike that balance. And a corollary, or like, what are some of the things that you're working on that industry isn't focused on?
One example of this is the work that I presented on learning symmetries. That work is kind of very early stages and one of our initial forays into the direction of trying to extract symmetries and that sort of structure from data. I don't foresee it being immediately impactful to industry in its current form, but I think that in the longer term, these sorts of techniques may be actually quite useful and quite impactful on real world problems. So that's one example.
Any addition?
Another example I could mention is some of the work we're doing on causality, where at this stage, we are only able to look at pretty small graphs with dozens of variables at most. We're testing it in environments that are very, very simple, far from the complexities that you would like in many real-world applications. Today, in reinforcement learning and many of these unsupervised sort of learning paradigms, you are typically working in simulated environments that are very, very simple, that have nothing of the complexities of the world, but still pose serious challenges. And I think it's going to take many years before we can grow the complexities of these environments to something closer to what applications need. On the other hand, I think the conceptual progress on understanding how you can build systems that are more robust, that can work out of distribution better, is of immediate application to industry, right? So, I can't presume what these things could be, but things like meta learning and in the right settings could be applied. But I'm thinking more broadly of techniques that can help. Examples that might have an impact fairly quickly could be new architectures that use attention or modularity or whatever. If these things work well in our little academic environments, there's a good chance they could also be applied in many industrial domains. But that is not the way that we're developing them. We're developing them in environments that are sufficiently under control and simple that we can debug and we can test theories and so on.
One other thing I'll add to this as well is a lot of the work that we do in robotics is on really basic motor skills, like playing with children's toys. And I don't expect robots that play with children's toys to be too useful or to be able to generate revenue, for example. But by studying those problems, we may be able to, in the future, discover fundamental challenges in artificial intelligence, which may lead to much kind of larger breakthroughs later down the line. It may allow us to better understand intelligence and what humans are capable of.
Okay, thank you. Any other question from the audience? If not, I will designate a questioner. Sung-wook Seo, are you there? Sung-wook Seo?
Yeah, I'm here.
Ask a question, please.
Hi, I'm Sung-wook Seo from Seoul National University, and I'd like to ask a question to Professor Chesterton. And first, thanks for the interesting work about the adaptive risk minimization, which seems to be more practical than other robot optimization work. But to my knowledge, this work assumes a test batch assumption where all test samples are drawn from a single group. So this might work well in some practical scenarios, like adapting the general model to a single end user. But however, there might be more realistic cases where we don't know the group information exactly at test time, and then unlabeled test samples can be drawn from multiple groups. So could you explain if this method still works in that case? And if not, how to deal with such heterogeneous test group samples for adaptation?
This is a great question, and the short answer is that this is an open problem and that we don't know how to solve yet. You're right in that the adaptive risk minimization framework is only going to be useful in settings where you expect to see unlabeled data from one part of the distribution, for example, from a new user, from a new region of the world, and so forth, which is often the case when you're kind of at a single point in time in a single place and you're seeing data from that part. But if your data is being shuffled, then we may need different frameworks for addressing that. It's also a problem that we're actively working on to try to address the parts of the distribution that our models are not good at and encourage the model to focus on those parts of the distribution so that it can improve on those more difficult examples. That said, I guess more speculatively, it may be that this sort of the sort of information about where in the distribution or where in the world you are is very important for models to do well. And the reason for this is that when humans take observations from the data, we see data in a very structured way. We see observations in time. We know the last observations that we saw. Things in time are very correlated. We're also always in the same place. The data that we're seeing are images. They aren't shuffled. We're always in one part of the world and in one point in time. And so it could be that to achieve the generalization that humans can achieve, we simply can't assume that all of our data is shuffled. We may need to make these sorts of assumptions that we're observing different parts of the distribution at different points in time. And that may allow us to achieve more robust models.
Thank you.
Okay. So do we have other questions from the audience? I see no hand there, so I would like to have the last question from Min-Young Moon. Are you there? Say something, please. Oh, maybe some sound problem there.
You hear me now?
Okay, we hear now.
Okay, sorry about that. Hello, I'm Min. I'm a researcher at State. I read the paper of the hardware lottery, very interesting. And the paper introduces the terms called hardware lottery to describe when a research idea wins, not because the idea is superior to alternative research directions, but it is more suited to the variable software hardware. And I think deep neural network is actually a good example since it was like introduced in 1980s, and like back then it didn't really get much attention, but now like it's everywhere, right? So my question is like, what will be the breakthrough of the modeling the world with the combination of hardware and software and algorithms? So to be more precise, like what will be the next hardware lotteries? Yeah, the question is to everyone.
The type of ideas that we have are very much limited by the type of tools that we have access to. So the idea, for example, that you can build a trainable system that is differentiable end-to-end by assembling modules is something that Yoshua and I have been playing since the early 90s, probably around 1991, 92. And it's been very powerful for us. And we were basically the only group who had access to a piece of software that was able to do this. Once Yoshua went to Montreal, he left AT&T and went to Montreal. He implemented in Montreal a system in C++ that could do the same thing, and then TNO, and then there was Torch and PyTorch. But the original system, we all had access to it all that. And it's one of the reasons I think that neural nets did not become more successful and more popular back in the 90s is that having this tool, this type of tool, was very difficult. You had to kind of build it yourself. It required a huge investment, and few people were willing to do this. And as a result, few people were able to really kind of play with neural nets of the types that we are working today. I think what has changed is now it's become very commonplace, even for companies, to release all their code in open source. And that makes all the tools available to everyone. That's really what allowed deep learning to take off. That plus, of course, GPUs and the availability of large data sets, plus, a few new algorithms. But the fact that the tools, became available, very widely available, I think is really crucial. So hardware determines what we can do. GPUs were instrumental. Software also determines to some extent what ideas we authorize ourselves to think about. I'm going back even earlier in the history. Why is it that people didn't invent backpropagation back in the 1960s? It's a completely obvious idea when you think about it, right? It's just chain rule, but people didn't think about it back then. It only started to be used for machine learning in the 1980s, and the reason is that people were using binary neurons, and the reason they were using binary neurons, there's several reasons, but one reason is it's very difficult with the hardware that you had at the time to compute weighted sums with neurons because multiplications were really expensive. If you had binary neurons, you didn't need to do multiplications, you just need to do addition and subtraction. And so the kind of hardware you have access to kind of limits your thinking. And good tools give you superpowers.
Thank you, Dr. Lukun. Any other?
And if I could add something, similarly today, I think the GPU architecture on which we depend may be forcing us into a style of computing that could close the doors to other types of architectures, for example, that involve a lot more sparsity. And dynamic routing of computation, for example, in principle should allow you to save a lot of computation. But on a GPU-like chip, you don't save anything. In fact, it might be more expensive because of memory access issues.
That and batching also. GPUs force us to
That's right.
basically process multiple samples that are exactly the same size in parallel because it's easier to parallelize. But it's horrible. It's overly constraining if you're dealing with things like sequences of variable length or graphs or dynamical structures. So yeah, current hardware really doesn't do what we need it to do yet.
Thank you. And I think it's time to wrap up all the program of today. So now we have reached the end of the day one program of Samsung AI Forum 2020. I am deeply impressed by the great talks and insightful discussion. Thank you, all speakers and participants. Congratulations again to the awardees of Samsung AI Researchers of the Year. The Day 2 program of Samsung AI Forum will start at 9 a.m. tomorrow in Korean time. Goodbye now, and I hope to see you next year in person. Thank you.